we get started with today's TrustML Young Scientist Seminar. Today we have 3 guests. Let me introduce our first guest, Salah, who is right now here to visit us in person. Salah has recently completed his PhD thesis at the University of Luxembourg and is currently a postdoc researcher at the Interdisciplinary Center for Security, Reliability, and Trust. His research focuses on practical solutions to achieve robust machine learning using self-supervised learning and multitask learning. His work lies at the intersection of software security and machine learning, with his recent publications presented in venues such as ICCV, IGCAI, AAAI, KDD, its Best Paper Award, and SP. Let's hugely welcome Salah to give his today's talk. Salah, please get started. You can also add more information.
Great. Thank you very much, Giunchiglia. It's also a pleasure for me to be here with you and to present my work. So indeed, I graduated last September from the University of Luxembourg. And apart from the pure research, I'm mostly interested in collaborative projects. So I do collaborative projects mostly with at the university. So I do some teaching, but I mostly work with in Luxembourg. It's very particular because we do research mostly with industry. So we work a lot with companies, and in 2021, I was mostly working with the hospitals of Luxembourg about COVID-19. And since this year, I'm working on a project, nature projects, that is more related to robustness for financial sectors. My interest indeed is mostly about AI and safe AI, either in healthcare and finance, but also I have some work on neural architecture research and multi-objective optimization that is very related to my actual work on AI security. So for people who don't know where Luxembourg is, it's a very small country located between Belgium, Germany, and France. So we speak more English and French and German. There is also Luxembourgish, but one speaks Luxembourgish in Luxembourg. Anyway, so I will move to my actual talk about. So my talk today will be about multi-objective robust machine learning for critical systems. In this talk, it will be mostly about my PhD thesis and my recent work. So I guess now you know that machine learning is used everywhere, and it's getting more, more pervasive in critical systems like autonomous driving, medical imaging, and even here for cancers or for gene detection and prediction. And recently, it has also been used to solve multi-objective problems like chemical component discovery. The issue here is that generally, when we talk about machine learning, we talk about most of the time supervised learning that requires a lot of label data. And in practice, what we do is we feed a machine learning model a lot of inputs and a lot of labels. And we hope that the machine learning the model will kind of learn the distribution that connects both. And at the end, when we provide it with a new input, we expect the machine learning model here, in the case of classification, to give us the right label. The issue with this approach is that it requires a lot of data. That's why we recently have been implemented what we call semi-supervised learning, which means that we still use some label data, and we create additional artificial data by removing information, which means that in practice, we do have access to the labels. Or here the task is to fill in the blanks in the text. And in this case, we have a first step, which is pre-training with a lot of data where we don't have the actual tasks. And then we have a second step where we use the actual label data to do whatever prediction we want. For instance, here it's a sentiment analysis task. So here we use a small set of label data to fine-tune the model. The issue with these approaches is that there are different ways to create this new label data. So in image, what I showed you before is about text, but you can also use semi-supervised learning in images by trying to predict orientations, trying to predict jigsaw puzzles, and other image transformations. And thanks to this kind of new data augmentation, approaches. We have achieved tremendous improvements in synthetic image generation. So this is what we got in 2014, and this is what we have in 2019. And more recently, with all the generative images model, we can even create from scratch images that follow some certain prompts. This was kind of the craze at the beginning of the year, of last year. Thing is, even if with all this improvement, we have achieved excellent results in terms of classification. If you take ImageNet today with the largest model, we have almost achieved perfect performances on this model. However, when we investigate the actual conditions before implementing such systems in practice, we see that we are still far from it. Because even if we achieved with more data machine learning, we still have an issue that is called robustness. So what is robustness? Actually, robustness is one of the last remaining topics that stops us from deploying this kind of machine learning system at large scale. There is actually no universal definition. So you can have empirical robustness, you can have provable robustness, you can have definitions depending on the communities, security community, machine learning community, software engineering community, each have their own definitions. But generally, what we try to define by robustness is the ability of the machine learning model to actually learn meaningful features, which means to be able to generalize to unseen distributions. So the unseen distribution can be synthetic one, a noisy one, adversarial one, or whatever. So there are different approaches that try to explain why a machine learning model are not robust. So we have the fact that scarcity, which means that we don't have access to all the data that we need to learn correctly the distribution. So this can be solved with semi-supervised learning because we are adding more data. We have also the issue of selection, which means that actually what we select between the train and the test does not cover the same space. So it can either because we have selected only a subset, or we have a population shift, which means the two distributions don't match. And in this case, we have the phenomenon of adversarial robustness, which means the ability to generate examples that are on the boundary that can cause decision shifts. And we can also find this kind of shifts in the natural world. And here we talk about generalization robustness in practice. So what is adversarial robustness? Adversarial robustness is the case where small perturbation can cause total misclassification or a misbehavior of the machine learning model in general. And in practice, how we do it, we start from some input, an image, for instance, and we try to compute a small noise that will be interpreted by the machine learning model and lead it to a different behavior. So, for instance, here, getting a misclassification with very high confidence. In practice, it's an optimization problem where we have to find the minimal, to minimize the perturbation. So the minimal amount of noise that we add that will cause a classification that is different from the original one. Thing is, in this case, we have the issue about what is the distance that we use, because depending on the use case and the task, the distance that is meaningful depends. Generally, in basic research, we use L2 or L-infinite distance, which is pixel distance, but we can also use perceptual similarity distance like LPIPS or SSIM. And in other cases, we can use even more tuned distance. The most common approach that we do is following a gradient. So we use different approaches that try at each step to find how to maximize the loss, which means going to an adversarial input. And this is what we call the PGG attack, which is one of the most established in the field. And since that time, so PGG attack is almost 4 years old. And since that, the community tried first to improve it. So trying to propose new attacks that are stronger and probably more computationally expensive. But at the end, we feel that these attacks do not really cover the real use cases. So once we move to the actual practical use cases, for instance, for sign recognition, or we can have face recognition and annotation, and image annotation, or even adversarial sounds, we see that here these problems require more constraints and more problem-specific information. in terms of distance, but in terms also on the algorithms and the information that we have on the model, because the gradient is not always available in this case. And more recently, there were also papers that have been investigating adversarial robustness in the medical settings, but in practice, not a lot of actual research has improved from the early adversarial attacks, even if the literature is pretty rich in terms of papers and research. So, in parallel of the attacks, researchers have also investigated ways to improve the models. So that's what we call robustification. The issue is that recent work have demonstrated that most of these attacks and defenses are not relevant. So they are very easy to break, either completely broken or using adaptive attacks, we can easily break them. So the question here is, can we do better than adversarial training, which is the most common approach? Also, it is a critical problem because today it's, in Europe at least, we have a new law that is being launched, which we call the EU Act, AI Act, that require companies from in 2 years now to ensure that any AI system that are implemented have acceptable risk or manages the risk that are related either to security or transparency or fairness. And adversarial robustness is one of them. So because of the criticality of the problem, but also because of the lack of real improvement in recent defenses, I have been investigating robustness of machine learning model, both against adversarial perturbation and natural perturbation, using real-world scenarios. So my focus was about 3 use cases that I will be presenting today. First one is with a major bank in France, and another one is about robot navigation, and finally about medical diagnosis. My objective here in my research is trying to find how to attack and also to protect models using minimal cost, which is computational cost, handling cost, and also drop of performance, because today we have kind of Pareto optimization. Whenever you make the model more robust, you generally lose some of its clean performances. So the common technique so far is what we call data augmentation, which is trying to add more training sets to your models, adding image transformation, or trying to do some mixture of inputs. But it's expensive because it just means that you need to add more epochs and to convert to learning that takes into account all these inputs. So what I proposed, what I designed is what we call knowledge recommendation. So the intuition of this approach is that instead of adding more inputs, we will add more knowledge to the model, either using expert knowledge, so working with an expert, or using more tasks for the same inputs. So for the first one is cover the input space, which means augmenting the knowledge using constraint. The second approach I will explain is augmenting knowledge using tasks. And the last one is augmenting the knowledge using physics. So let's start with the first one. So this first work has been done with BNP Paribas, which is a bank that works on different topics, including DevOps and AI. And their problem is that they don't really have scientific experts. They mostly have law or financial experts. And they are transitioning to machine learning model. So far, they have some of their systems that have actually been deployed in production using AI and using machine learning, like fraud detection and money laundering. And the regulator here in Luxembourg, they kind of impose on them some criteria to ensure that their system is reliable, like interoperability, privacy, and robustness. So my focus was about robustness, working with them. And I worked on credit scoring and money laundering. So I will show the result for credit scoring, at least for now, because it's public. And what we showed with this work is that the model that they have deployed in production are very good according to the common metrics. So the AUC on the test and the train. It uses gradient boosting and ensemble and random forest mostly, and it is sufficient for the needs. The issue of this approach is that it needs to minimize the cost of the bank, but also the safety of the bank, which means that imagine that you are a company and you need money because it's credit scoring is kind of way of bank to allow loans to other companies or other organizations. So the machine learning system, we have to, whenever there is a new request, to analyze the past transaction, to do some time series analysis, do some feature engineering, and finally do a classification to decide whether the model should or not accept this kind of transactions. So if we want to assess the robustness of this machine learning model, we can assess it at each of the levels. So we can assess it at the first level, which means trying to simulate all the transactions using business simulator and looking at all the pipeline of the bank. But this is intractable because it's very expensive for them. Another way that we can do it is only working on the machine learning model. So this is the white box setting that researchers focus on. So we just work on the features, the machine learning model, and look at the output, but it is not realistic because it does not take into account the domain expert knowledge, because there are some features that cannot be perturbed in any ways. There are relations between the different features in the banks, and there are information that cannot be changed because they are computed internally by the bank. So the attacker doesn't have access to this kind of information. So we need some intermediate level that will take into account the space that is constrained, that cannot be achieved by the attacker. So this is what we developed with them. So the idea here in the approach is that it's in between. We take past transactions and we start from some new transaction that is realistic and acceptable, but is rejected. And our objective is to, again, using similar approach to adversary attacks, to create a small noise that will stay, that will give us a transaction that gets accepted, but it needs to be realistic. It needs to be small, in a sense that it should not be noticeable by the human expert that we validate on, and it needs to maximize the amount of the money that the attacker will withdraw from the bank. And this is what we get. So at first, we investigated different approaches using different search approaches, but also gradient-based attacks. And at the end, we designed a genetic algorithm based on energy tree that will optimize the different objectives that we defined. And these objectives have different weights that can be either optimized using Pareto objectives, or they can be optimized with the domain experts. So again, the objectives, the fitness function that we have are about the misclassification, so causing the attack to succeed, but also the perturbation size, and finally, the amount of transaction that we need to maximize. Oh, yes, and of course, the constraint validation that needs to be minimized in a way that the features that have been that can be attacked and the relationships between the different features are preserved. So for instance, those are some kind of constraint that we have. If we have a constraint between three features, we can transform it into a fitness function, which can be optimized during the attack process, the search process. So if we compare the original result that mentioned that the attack that exists are very successful, when we take into account all the properties of the system, we see that the actual success rate is pretty low. So it drops from about 80% to 0% if we take into account the properties of the model. But so this is the literature, what existed in the community. And what we propose, thanks to our approach that we call Coeva, we were able to generate 8%. We moved from 0% to 8% success rate, which is still low, but remember that in practice, it means that for every 12 transactions, the adversary can create a new one that is adversary, which means that in practice, the result that we got were pretty bad for the bank, in the sense that the cost to generate attacks against their system was not that high in practice. Then we included this search optimization during the adversary training process. And we demonstrated that combining both, so traditional adversary training with this search for constrained adversary examples, leads to totally robustifying the machine learning model, which means that using this approach, once we try again to attack the system using gradient-based attack or search-based attack, we cannot manage anymore to generate adversary examples. So the takeaway of this part is that if we is going from the scientific literature to the practical domain, we can see that the conclusion that we have, that we assume are not valid anymore, and we need to take into account the domain knowledge, for instance, as constraints. The second way of taking into account domain knowledge is what we call task augmentation. So in task augmentation, we use the paradigm of multitask learning. So the idea here is that we start from one multitask learning is generally using one shared encoder. So we have layers that are shared across different tasks, and then we have specific tasks. And these specific tasks can either be main task, which means that this is the task that we are targeting, that we want to use at the end, and some can be auxiliary, which means that they are here only to optimize or improve the learning of the main task. So the research question that we covered here is first to study whether multitask learning actually affect the robustness, and also to see whether we can use self-supervised tasks, which means artificial tasks, to improve also the robustness of the model. So we start with a definition of vulnerability. So the vulnerability of a model is just a way to explain how much the loss will change when we add additional tasks. And we provide two theorems. The first one links the vulnerability of the machine learning model to the orientation, so the gradient orientation of the different tasks, which means that if we manage to train a model with tasks that are very uncorrelated, the machine learning model will become more robust. We can also see that so this is the first one. And the second theorem tells us that it's not the total number of tasks in the model that will affect the robustness, but mostly the marginal vulnerability of the tasks that we will add. So it guides us in the second part in the selection of the tasks that we can add to improve the robustness. So here for the empirical study, we did it on what we call on data that is called taskonomy, which is a robot navigation task, robot navigation model that has multiple tasks that range from image segmentation to orientation to edge detection, etc. And the idea for us was to study how the number of tasks impacts the robustness. And we focus on 5 different tasks. So some of them are highly correlated, like the Euclidean distance, the Euclidean depth, and the Z depth. Those are tasks that use different ways of measuring the distance and the depths and are very highly correlated, but we also use tasks that are not related at all. So what we get is, as we have in the theoretical part, some specific tasks, when they are added, can have can cause a drastic drop of performance in the adversarial robustness of the model, which means they increase the vulnerability of the tasks, and some can be leveraged to decrease the robustness, to decrease the vulnerability of the model, which means that if we are trying to target a task that we know is weak, like semantic segmentation, we can try to mitigate this drop of performance by finding the right combination of tasks. The only issue that we actually have is that adding more tasks can become also more expensive. That's why, so here it's just empirical results where we have the diagonal or the single task model, and we have an improvement for each main task. We can always find one task that's one auxiliary task that we improve over the single task model. We also demonstrate that not only the selection of tasks is important, but also how we weight the task, which means that we can also mitigate the vulnerability of models by a smarter way of weighting the tasks. So we have a drop of vulnerability from 1929 to 550 and 688 to 165 for the norm task. These results are also generalizable to adaptive attacks. So even if the attack takes into account the gradient or to assume whether it's a gradient masking phenomenon, we also demonstrate that it works pretty well. So now that we demonstrated that multitask learning can be used to improve the robustness, the question is, can we push this even further? Can we drive the multitask learning to become robust? So the proposal that we have, which is the work that I've been working on with Jinfen, is about during adversarial training process to artificially add new tasks and then orient the gradient learning towards the path that will achieve the highest robustness, but also clean accuracy, which means that at the end we have multi-objective optimization. So it's an approach that is called MGDA, multi-gradient descent that will find the path that combines will at each iteration of the attack and each iteration of the training, we will compute the right weights that will find the optimal path to achieve the best clean performance on the target task and the best robust performance of the target task, taking into account clean and adversary example. So the idea of this approach is that we know that the angle, the covariance, which is the orientation of the gradient, is important. Can we force it to be in the right way? And what we show here is that if we select some smart semi-supervised tasks, like the jigsaw, the rotation, the histogram of gradient, and the depth estimation, if you combine them, we can manage to find optimization that perform much better than data augmentation techniques. So I will move to the actual results. So if we do just the adversary training alone, which is the common approach, we achieve about 40% robust accuracy. And if we use the right tasks with ATA, we can achieve much higher robust accuracy while preserving the standard accuracy. But what we also show is that these approaches also improve the robustness to transfer attack, but can also generalize to adaptive attack and larger models. Finally, we also demonstrate that we can use dense tasks like autoencoders, histogram of depth, histogram gradient and depth on larger datasets like Robin to achieve also significant improvements in robustness. Going back again to the practical use case of this approach, because as I mentioned, in general, we do adversary training with large data sets, so we do data augmentation. But there are cases where we can't do data augmentation because it doesn't work. For instance, generative adversary network to create artificial chest X-ray have all been discarded by experts. So we are not able today to generate images that are domain specific. So for instance, for this case, adversary training with data augmentation cannot work. But our approach, for instance, if we do for atelectasis with the gender, so if we do multitask adversary training between the gender of the patient and the atelectasis pathology, we can improve the robustness from 50% AUC to more than 80% AUC using this kind of approach. So the approach that we propose is very well designed for cases where data augmentation using generative images or unlabeled data is not feasible. And we also demonstrate that surprisingly, not only it improves adversary robustness, but it also improves generalization robustness, which means with this approach, if we train the model on Shakespeare data set and we evaluate in IH, while general approach have a significant drop in performances, ours mitigates this case. So the takeaway here is that we can, if we don't have access to more data, we can improve the performance and the robustness of the model by adding additional tasks and tuning the training in a smarter way, I would say. And surprisingly, it improves both adversary robustness and generalization robustness. The last part of the talk will be about improving the robustness using physics. So what we call physics-informed augmentation. See, in this case here, instead of adding knowledge in the input or in the task, we add it at the later stage by taking into account physics operations. So physics are very common in phenomena like simulating light emission or the waves, or even in COVID. During COVID, the first models were using epidemiological models that are either agent-based models or equation-based model, which is the case here. And the idea was whether we can use this knowledge that has been accumulated in the last 20 years in epidemiology to combine it with machine learning models. So yeah, COVID is still here. And as I mentioned, as part of this project with the government of Luxembourg, we have been working since 2020 about trying to build tools to do prescription, which means we need to not only forecast the evolution of the pandemic, but also be able to provide insights and recommendations of how to mitigate both the health impacts and the economic impacts. And for this case, it was 3 steps. The first step was about forecasting. So this is the general problem of trying to predict how the pandemic will evolve at early stage for a country that is pretty small, because Luxembourg, in total, we have 600,000 people, so not a lot of data to work on. And the early stage of COVID, it was moving very quick and very fast. So the distribution shifts of the behavior we're analyzing was pretty quick. And the second one, once we have this model, can we find optimal scenarios to control the pandemic while keeping the best economic outcome? So the proposed framework that we have is 3 components. So again, here it's a combination of machine learning, epidemiological models, and search algorithms. So for the first part is building a machine neural network that takes into account time series of different inputs. So we take into account country-specific information like demographics, but also we take information from other countries that can be beneficial to our own model. The second part is using the epidemiological model that was commonly accepted. So it's kind of states. We have different states where the people can go from healthy to sick to dead or recovered. And then finally, once we combine these two, we'll put on top of it a policy search that uses a genetic algorithm to find the optimal mitigation scenarios. So why did we kind of over-engineer this approach? Because techniques that were used at that time, curve fitting or ARIMA techniques, or even a recurrent neural network techniques that were proposed in previous papers, were very good at short-term prediction, but they were giving totally unusable results when we go to more than 2 weeks data, 2 weeks forecasting, which is what actually we need for this kind of pandemic. So yeah, so those are the different techniques that we tried and we compared to, and they were not working good enough. So what we went to for the machine learning part, it was a very simple model at the beginning. So it was just a neural network that we feed-forward neural network that we extended with some special feature engineering that uses mobility data. So we took into account the data from the different from Google and also from Bing about phone connections. So we were able to know whether people were using transport, were going to groceries, going to schools, etc. And then we added some demographic information to take into account also the specificity of each country. And at the end, as you can see here, we are not trying to predict the death or the cases, which is very different from every other approach at that time. Here we were predicting the RT, which is the reproduction number. It's the main hyperparameter of equation-based model. So once we have this RT, it's the one that we inject directly in our epidemiological model to run it into the differential equations of each step. So we inject this output into this layer, and this epidemiological layer at the end is the one that will forecast us the cases, the deaths, etc. Why do we do that? Because working with the RT for the machine learning model is much easier to learn and trying to forecast all these states. So this is the first advantage. And the second advantage is that because the state-based models are very well established, we know exactly how to debug them, to understand them, and they are very easily explainable, which means that at the end, I can, when I was doing demonstration to the government, I was capable of explaining to them what is the impact of each parameter, how they can play with it, and how they can justify and motivate their decisions. So at the end, when we combine this approach, we can get very good performances even using simple neural network. And we also demonstrated that this approach is very well generalizable, because when we do region splitting or random splitting or time splitting, we always get very good results. So the last step is what I mentioned, which is proposing mitigation scenarios. So the idea for us is that once the policymakers can define their constraints and their objectives, there is a search algorithm that will optimize different parameters of the machine learning model and try at the end to give a schedule. So what we provided the government was data like this, so a schedule of different scenarios where they can close schools, or they can close hospitals, or they can close different components. And based on that, it will affect how the machine learning model will forecast the pandemic. And surprisingly, what we found out is that that some of the scenarios that were proposed, some Pareto scenarios that were proposed by our approach were much better than what was used by the government or in France and Luxembourg about the progressive and cyclic closures that were established. So the main takeaway here is that when we have a complex problem, we don't need to try to predict all the complex outputs. We can use intermediate knowledge that's from domain expert to enrich the model and reduce the noise and improve the generalization of the approach. So to sum up all this, so here my research so far is about knowledge augmentation. So how to improve the robustness without adding data. The main takeaway here is that you can, if you don't want to add input, you can add constraint, or you can add tasks, or you can add domain knowledge using physics with surrogates instead of adding new data. And this work has been published. So for the first part, we have 4 papers and 2 for the last one. And actually, I'm still working on the latent space work because we have some interesting idea to go deeper. Apart from this research about adversarial robustness, my focus is also about neural architecture search. Again, neural architecture search is how we can generate new architectures of machine learning models that will achieve some properties. So I have some papers about achieving high robustness by finding simple components, combinations, and also usage for adversarial attack in privacy and watermarking, which is a way to have different use case where we can where the objective of this approach is to use the noise not to change the prediction of the model, but to be able to track the source and the authenticity of the assets. This can be used against a deepfakes approach or against a generative image approach. Yeah. And finally, as I mentioned, my work is about trying to build machine learning model that is practical, robust, but also robust in real life. So one work that we are submitting this year is about human perception of adversarial attack on text. Because there are, in the last 5 years, there are a lot of research papers that propose new attacks to cause misclassification, but very few actually evaluated the impact on humans. So what we did is we did a large human study of around 400 people. We evaluated 9 attacks, and we demonstrated that actually all of them are pretty bad. Actually, they are very easy to detect and cause a lot of grammatical issues. And when we compare the claimed approach success rate in the papers with the human success rate, there is still a lot of work to do in this approach. So our motivation here is to demonstrate that what we use as a researcher as success criteria for research can be very far from what is expected from human operators. Another work that another of my work is for, again, here we're trying to use physics for adversarial attack. So instead of changing the pixels, we are working on a simulator. So we have a simulator that can generate chest X-ray images based on real 3D models. So we have 3D models where we control the density, the density of each tissue, of each bone, etc., the age, the orientation of the patient. And we studied what are the criteria that affect the performance of the model. And we demonstrated that depending on the pathology, some of them can be very affected by the power of the machine, or the gender, or the age, or the position of the human during the scan. So this is a work that we try to bridge simulation and generalization research into a practical use case. And finally, another work with Jinfen is about robustness of foundation models. So foundation models are models that we use pre-train, and then we reuse in many components. For instance, you have super resolution models that are used in generative network. So super resolution models take into account a small image, and then they try to extend it, and then we can use it for either to do classification or any downstream task. The issue in this research, because the models now are so big, they don't train everything. So they reuse pre-trained components, and then they combine everything. The issue is that if the components themselves are vulnerable, it can cause all the system to fail. So my research now is trying to see whether protecting or robustifying individual components can be relevant to the downstream task. And some of our results demonstrate that no, the models that are provided and claimed are robust, are not in practice, and we propose a better approach to adversely fine-tune these models. And that's it for me. Thank you very much.
Thank you very much. Hi, audience. If you have any question, please ask. Okay, please.
Thank you for your really nice and informative talk, and I don't know company. Just a few small questions. The first one, could you go back to your third part, which is there's one, yeah, please do it. The Oswald, sorry. For the page. The Oswald. Yes, this one.
Yes.
I'm just really curious because Oswald is meaningful when we're measuring how much variation is factored and explained by your model. So I'm wondering why here you choose to use Oswald on the other features.
Yes. So what we try to provide here, in the actual paper we provide R-square, but also confidence intervals that are provided for the practitioners. The R-square was mostly used because the previous literature was using it, so we had to use the same metric to be able to compare. So in the study, we mostly the main results that we provide are with confidence intervals that are more meaningful. But again, just for the literature, they won't nice tables so we have the same metric.
Then the other question is can you go to I saw something related to when you're comparing the arena. So yes, please. So here, if I understand this right, you're probably just saying that when you're using the model, you're actually the long-term that's the long-term. So the models when you're comparing this, they actually offer the shorter ones. One that if you compare with the long-term, the long-term baseline, so for example, the university ones.
What we compare to are mostly time series machine learning models that were available at the time, so mostly ACM and gated techniques. And we used ones that were designed for short-term and mid-term, but not specifically approaches for long-term time series forecasting at the time. So I would say we use as baselines ones that were common in the literature, but I'll be very interested if there are more recent approaches since 2020. Sure.
And another one is, sorry, the last one.
No, please.
The last one is can go back to the first. Sorry, the research question one is yeah, so you also just about wondering that how can we explain the difference between the counterfactual explanation and the robustness, because in counterfactual explanation, you're also trying to have a specific result that you could find. And you're trying to have a small prediction as well to try to shift the previous input to this level or counters. But in terms of the robustness or sorry, robustness, I would say
I'm not sure to understand the question, but I feel that it's just different wording for the same phenomenon, I would say. Because again, if you take even the software engineering community, other examples, we call them test cases. And in another community, we give them the same different words. But I think the actual process, which is finding the minimal changes that will cause a different behavior, is pretty universal. Just that if you take security community, they talk about threats and vulnerabilities instead of talking about the word that we use. I'm not sure, I don't know the words that you are using. I feel it's just different communities and different words.
Because this question is already discontinued. So there is one thing on the actual explanation of words that trying to explain what's the difference between them. And they're trying to say that when you're using the concept explanation, then you're going to see what's the minimum real or realistic observation to change the the previous input to the it's the same thing.
Yeah, so for me, it's different wording to talk about adversarial, counterfactual examples are adversarial examples, are test cases, are ML vulnerabilities. But I really feel that depending on the community, they use different words. But I think it's the same.
I see. Thank you, Salah. Then I have no questions. Thank you so
But
much.
I'm really interested in the paper as well.
I'll send it to you.
Thanks.
No worries.
Yeah. Have further questions? Well, let's see. And our audience have it. Perhaps not. Maybe then we can proceed to our next speaker.
Sure.
If she's here now.
So Eleonora has recently completed her PhD at the University of Oxford under the supervision of Professor Luxembourg. And now she's doing a postdoctoral. She's a postdoctoral researcher at UV. Her main research is about neurosymbolic AI with the focus of how to use neurosymbolic techniques to make deep learning models safer. So it's the intersection between AI safety, neurosymbolic AI, and her recent work also about constrained AI. And her work has been published in various top-tier conferences and journals, and she won multiple awards with her work, especially, and the most recent one was about road air that she will introduce later on. So I'm very happy to have Eleonora as one of my first guests, and looking forward for your talk.
So thank you very much for your very nice introduction. So yeah, as Salah said, I am Eleonora. I'm currently at Vienna doing my postdoc, and I'm also a visiting researcher at the University of Oxford. And today I would like to give you basically an overview of deep learning with hard logical constraints, which basically has been the topic of my research for the past, I think, 3 years. So I would like to start with a brief outline of my talk today. So I'll first start with an introduction in which I will cover why this problem is important and why we should study more deep learning with hard logical constraints. Then I'll start with the simplest type of constraints that we can find, which are hierarchical constraints. I'll then basically extend our syntax of the constraints, and we'll go through more complex constraints, namely normal logic constraints. And I'll then present exactly RODAR, which was the paper Salah was mentioning, which is basically a novel data set that we proposed for neurosymbolic models. I will then conclude with the open questions in the field and the possible future directions that we might take. So what is the problem? As Salah mentioned, deep neural networks have been responsible for state-of-the-art results in many different fields at this point for many different years, right? However, it is still the case that they can exhibit unexpected behavior and make mistakes that an intelligent being would never commit. Some of these mistakes are so bad that they actually make the headlines of some major newspapers. So we have, for example, the case of Google telling people that the air was very safe to breathe in Sacramento, when in reality there was a fire going on, and so the air was very polluted and it was actually very not safe to breathe, essentially. Another very famous case was the case of Compass in the US, where essentially a black box model was used to decide whether people could have access to bail or not. And essentially people didn't know why they were giving a certain sentence. And then probably we have the most famous case of neural networks being used in Tesla and actually causing car crashes, even in situations which seemed very safe. So all of these mistakes, all these errors would have never been committed by a human being. So what is the main takeaway point here? The main takeaway point is that neural networks are great. They have achieved a lot, and they have allowed us to break a lot of open problems, let's put it in this way. However, they can still make a lot of very basic mistakes, which, if when applied in high-stakes scenario, can lead to actually like big damages, even to the point to killing people. So how can we try to at least starting addressing this problem? Well, the intuition behind my work is that for most of the problems that we have to handle, human beings have collected a huge amount of background knowledge. And so the idea is to use this background knowledge to sort of constrain the learning of the neural network itself. So what is the goal of my research? The goal of my research is to build the neural networks that are guaranteed to be compliant with the background knowledge that we have about the problem, and that at the same time can learn from the constraints themselves. So if we take, for example, the example of autonomous driving, we want a neural network that is guaranteed to stop if a pedestrian is crossing in front of you, and at the same time can learn this idea that going over pedestrians is probably not a good idea. So the question now that we have to ask is it possible to achieve this? And the answer is yes. However, we need to make some assumptions on the syntax of the constraints we are expressing. So this is still a very general question, right? And being researchers yourself, you will know that this is too broad to be tackled. So I needed to narrow it down. And in particular, I decided so far to focus on multi-label classification problems. Why multi-label classification problems? Well, for three main reasons. The first one is that it is possible to assign a human understandable semantics to the output. Secondly, there often exist correlations among these outputs, and we have background knowledge about such correlations. Thus, what we can do? What we can do is we can write hard logical constraints that define the admissible output space of the development model. Okay, so this is our my research question. Let's now start with the simplest problem we have tackled so far. So just to give you a very basic idea, let's take the simplest problem we can have. So in the simplest problem we can have, we have just two classes, A and B, and the simple constraint, A implies B. What does this constraint tell us? Well, this constraint tells us that if we predict the label A, then we must also predict the label B. So no matter what, if we predict A, we must also predict B. To put you, like, to give you an example, you can imagine a image classification task where you are given multiple labels, and among these you have zebra and animal. Now, you want to have a model that whenever it's predicting zebra, then it's also predicting animal, because as you can imagine, it wouldn't make any sense to predict the zebra for an image but not animal. So this is like a conceptual example. Let's now try to visualize the problem as well. So this is a data set, a very simple one, where the class A has this distribution. What does this image tell us? Well, what it tells us is that if a data point falls inside this rectangle, then it belongs to the class A, so it needs to be labeled A. And if it doesn't, then it doesn't belong to the class A. Conversely, for the class B over here, what we have is that if a data point falls in either of the rectangles, then it belongs to the class B, and if not, then it doesn't belong to the class B. Now, as you can see, in this data set, the constraint is actually always satisfied, right? Because whenever a data point falls inside the class A, then it also belongs to the class B. So how would we approach this problem with a standard neural network? Well, in the standard approach, we would most probably take a simple feed-forward neural network, or any neural network that we like, actually. And this neural network would have two outputs, one for A and one for B, right? And then we would have some sigmoid and nonlinearity at the top, and we would train this with the binary cross-entropy loss, right? So what is the problem with this basic approach? Well, the problem is, firstly, that there are no guarantees that the model will actually satisfy our constraint. And secondly, the neural network has no knowledge about this hierarchy, and so it cannot exploit it to its advantage, right? So to actually give you an idea of how it would, a very tiny neural network would perform, I actually implemented a simple neural network with one hidden layer and 7 neurons. And here on the left-hand side of the slide, you can see what are the decision boundaries for this neural network. Now, as you can see, with a very tiny neural network, we have that like the model is actually struggling to learn these two rectangles, right? Because how do you read these decision boundaries? So the bluer a zone is, the more confident is the neural network that the data point falling in that area belongs to the class B, let's say over here, while the redder it is, the more confident it is that it doesn't belong to the class B. Okay, so here we have seen that if we take a tiny neural network, then this actually struggles to learn even this simple distribution. So let's see what we did. What was our solution? Well, our solution was very, very simple. So what did we do? We took exactly the same neural network, okay? And then we build what we call the max constraint module on top. What does this max constraint module do? Well, this max constraint module that you can see over here, it does simply this. It leaves the output for A completely unchanged. And then for the output of B, it takes the maximum between the output for A and the output for B. Now, what this allows us to do? Well, essentially, it ensures the satisfaction of a constraint, right? Because no matter what is the threshold, we will always have that the output for B is actually major or equal than the output for A, right? If you have any questions at any point, just feel free to stop me. Okay, so if everybody is on board with this, what is the problem of using this very simple layer on top? Well, the problem is that it can cause wrong supervisions. What do I mean by this? So suppose we are in this scenario. We have that the output for the class A, so the initial output of a neural network before the layer, is greater than the output for B. Also, suppose that the ground truth for A is equal to 0, while the ground truth for B is equal to 1. Now, what would happen here? So if we think about the standard cross-entropy loss, we would have here that MCM of A would return the output for A, and it would teach the neural network to decrease the output for A. However, the final output for B after our max constraint module would be equal of H of A. And thus, what it would happen is that this H of A would be supervised by the positive label Y of B. And so we would actually teach the neural network to both increase and decrease the output H of A at the same time. So this actually can lead to wrong supervisions, right? How can we fix this? Well, luckily, we didn't need to come up with some very fancy solution. There was a very intuitive way of fixing this problem. So this is the loss function that we came up for this simple case. As you can see, this is very, very similar to the standard binary cross-entropy function. So let's break it down a bit. So let's first look at the loss for the label A. So as you can see here, this is the standard equation for the binary cross-entropy loss. Nothing changes. Let's have a look at what happens on the other end for the loss for the label B. So let's break it down. case by case. So let's first look at what happens when the ground truth is equal to 0. Then what we have is that this is this term over here, which again, as you can see, is exactly the same as the standard binary cross entropy law. Now, where do we have the change? We have the change over here, when the ground truth for B is equal to 1. In this case, as you can see, we pass again essentially this equation, but we slightly modify it. And what do? We simply multiply the output for the class A to its ground truth. So as you can see, now if we have the ground truth equal to 0, then this would just return h of B, and we don't have any wrong supervisions anymore. So this, let's see how this solution actually pans out in our simple example. So if you remember our example, we have the two classes, the constraints, and these are the decision boundaries obtained by the very basic model. So how would our neural network do? So these are the decision boundaries that we managed to obtain with the exactly same neural network, 7 neurons trained with the exactly same learning rate for the same number of epochs and everything. The only difference is that we add the simple maximum on top and this modified version of the binary cross entropy law. Okay, so the question is now obviously, how come that with basically the exact same neural network with just a maximum, we can achieve such better decision boundaries? Well, the answer lies in the fact that we need to look to understand this phenomenon at what happens right before the layer itself. So after the layer, we have the decision boundaries on our left. However, if we look at what happens before the layer, we have the following decision boundaries. What is interesting here is that what the neural network learns to do is to delegate the predictions for those data points that belong to this tiny rectangle to the class A. So what essentially does then is doing the maximum between this area, which is 0, and this area, which is 1, and you get the final decision boundary, right? So essentially, we have let's put it this way, more efficient usage of our neurons, right? Because the neural network doesn't need to relearn that here it needs to output 1, because the prediction on the class A is sufficient to decide that this is 1 as well. Okay, so in this case, actually using this hierarchical knowledge proved to be helpful. However, what happens in a scenario where we don't need this background knowledge? So suppose that we have this following data set. So we have simply moved this tiny rectangle, which was first outside of the bigger one inside. So in this case, what we have is that the class A will be this tiny rectangle over here, while the class B will be the bigger one. What happens in this case? Well, in this case, the neural network is again able to approximate very well this, both like the rectangles and the very clean decision boundaries. Notice that in this case, the neural network didn't delegate the prediction to the class A. So what is the takeaway point here? The takeaway point is that the neural network can decide when to use the background knowledge and when to basically ignore it, with the advantage that in this case, no matter what, since we have a maximum, the constraint is guaranteed to be satisfied. Okay? So this was the very simple solution with just one constraint. Now, what happens when we have n constraints, thousands of constraints? Can this approach be easily generalized? Well, the answer is yes, because suppose that we have many constraints, then for each label A, we just need to take the maximum between its own outputs and the outputs of all its own subclasses. And for the constraint loss, we just need to apply the same trick over here of multiplying the ground truth by its own output. So as you can see on a GPU, this max constraint layer, we were able to actually implement it with just a single operation, while the max constraint loss with 2. So it was very easy to implement it on a GPU. This is just a table that shows you how well this approach does in practice. So all these 4 are actually models that were developed exactly for hierarchical multi-level classification problems. And in particular, these 2 are very convoluted neural networks whose topology is sort of mirrors the hierarchy of the constraints. And these are a lot of different data sets. These ones are on function protein predictions. Some of these are on text classification, image classification. And what was really mind-boggling for us was the fact that we managed to beat all of these models most of the time with simple feed-forward neural networks with just 2 hidden layers and our solution on top. So this really proved the effectiveness of our approach and the importance of using this background knowledge into deep learning algorithms. So this was the case for hierarchical constraints. Now the question is, can we actually have more complex constraints, right? Because as we can see, the hierarchical ones were very limited. So what is, first of all, a more complex constraint? A more complex constraint is a constraint written as normal logic rule, for example. What does this mean? A constraint written as a normal logic rule is a constraint that is written in this way. And what does this tell us? Well, it tells us that if a data point is associated with the labels A1 to AK, but not with the labels AK plus 1 to AN, then it must be associated with the label A. So what is the goal? What do we want to do? Well, again, we want to essentially bring the same basic intuition that we have applied in the hierarchical case and see if it works for these more complex constraints. So we want essentially, again, to build a constraint model on top of the neural network. Given the constraints and this initial neural network, what do we want to achieve with this constraint model? Well, obviously, we wanted to achieve to get a final output that is coherent with our constraints, right? However, given these type of rules, we could put everything equal to 1 and we would achieve coherency, right? So we want to have some more properties for our output. So we want our output to also be supported relative to the initial set of labels and the set of constraints. What does it mean to be supported? It means that each label that is in M must be either in H, or it must be, it can be derived from the application of a chain of rules. It must be also minimal because, again, we don't want it to like converge to the basic solution where we put everything equal to 1 and our constraints are satisfied. And it must be unique. Why we want uniqueness? Well, because given an initial set of labels H, we want to be able to deterministically decide what is our final output. So the question is, can we achieve this goal using the same intuition that we have used for the hierarchical case? So this is, again, as a reminder, what we have done in the hierarchical case, right? Now let's take a problem with a simple normal logic constraint. What would we do in this case if we have one simple constraint? Well, given this constraint, A and not B implies C, how do we read this? That if a data point is associated with the label A but not the label B, then it must also associate it with the label C. So if we use the same sort of intuition that we use for the hierarchical constraints, what we should do would be, we leave the output for the classes A and B completely unchanged. And then we set the final output for the class C equal to the maximum between the output for the class C itself and the minimum between the output for the class A and 1 minus the output for the class C. Now, how do you read this minimum? Essentially, if you are familiar with fuzzy logic, this is nothing else than the translation of A and not B in the Gödel norm. Now, if you do all the calculations, you could see that if we use this sort of formulation of this final layer, we actually are guaranteed to be compliant with this unique constraint. So, was it this easy? Unfortunately not. Why? Because this intuition doesn't work when we have multiple constraints. Let's see why. Well, the first problem that we had to face in this setting was the fact that now we are allowing for circularities, which weren't allowed in the hierarchical case. Now, this problem, if we simply follow what we have done in the hierarchical case, what would we do? Well, given these two constraints, we would set the output for the class A1 equal to the maximum between the initial output and the output for the class A2, and this in the same way for the class A2. Now, if we use this formulation, we have a problem that this equation has infinite solution, right? However, it's a very easy problem to solve because we can just put the final output for the classes A1 and A2 equal to the minimum of the set of the tuples of values satisfying the equation. So we just do the maximum between H of A1 and H of A2. So very easy to solve. Was this the only problem? Unfortunately not. Why not? Because we are allowing for a negation. So what happens when we have circularities within a negation within a circularity? Let's take again a very simple example. In this case, we have not A1 implies A2 and not A2 implies A1. Now let's follow what we have done exactly here, right? So in the hierarchical case, if we follow exactly what we've done in the hierarchical case, what we have is that are these two equations, right? Now one could think, oh, wait a second, I could just again do what I've done in the case of a positive circularity and just replace these two M's with H's, right? However, if you do this, suppose that the initial output of a neural network are two zeros, so you have maximum between HA1 and HA2 and 1. So what would happen is that we would start with the neural network would tell us, look, I think neither of the labels should be predicted. And if we apply the layer, we end up in a situation where we're actually applying both. So this would make no sense, right? So we would lose essentially our minimality and supportness properties that we wanted to have. So unfortunately, this problem cannot be solved using this formulation, and we needed another assumption, namely that the set of constraints needs to be stratified. What does it mean that a set of constraints need to be stratified? Well, this is a concept that comes from logic programming, and it simply means that if we draw this dependency graph, there cannot be a circularity involving a negative edge. So unfortunately, if we'll ever have a situation like this, we cannot incorporate these constraints in our model. However, so now we have this assumption, we can still do quite something, right? So here on the left is simply a very scary representation of our final model, and this is a representation of what happens in each one of these layers. And here on the right, I would like to guide you through a simple example. So suppose we have these two simple constraints. If a set of constraints is stratified, it means that we can divide it in groups, as you can see here. So each one of these is essentially a group of constraints, which we can essentially compute together, okay? And it defines us the steps in which we need to compute the labels in the head of each constraint. So if you want more details on how this stratification is done, is all in the paper, or we can discuss it later. So given these two constraints, what we need to do is we can come up with sort of this grouping. So what this grouping tells us is that initially we need to compute A, right? And since it doesn't appear in the head of any rule, we just leave it unchanged. Then we compute the output for B. How? By taking the maximum between its own initial output and the final output for A over here. Finally, we compute C, the output for C, which is the maximum between its own initial output and the final output of B. So with this idea of stratifying the computation of the output, we are actually able to include the negation in the body, multiple elements in the body, and we are actually guaranteed to have a solution that is unique, satisfies the constraint, is supported, and it's minimal. So now here we have again done a very extensive experimental analysis on, I think, 15 data sets, and we have compared with a bunch of baselines. And again, we have also measured this using 6 different metrics. And again, we managed to beat with some state-of-the-art models or some baselines using simply feed-forward neural networks with 2 or 3 hidden layers. So again, this proved that actually using this background knowledge during the training of deep learning models can not only give you safer solutions, but it can also actually improve the performance. So now finally we go to the lighter bit of the talk, where I just will describe to you the novel benchmark for neurosymbolic models. So as you could see, all the models that I've proposed so far, they were testing on a lot of data sets. However, the problem that I faced was that I didn't have a killing application, a realistic safety critical data set, which was annotated with logical constraints, with which I could really prove the importance of developing this method and how neurosymbolic models can help in actually realistic scenarios. So how did I solve this dilemma? Well, together with my team, we created the first autonomous driving dataset with requirements expressed as logical constraints. So how did we do this? Well, we partnered with a group that was focusing on autonomous driving and that actually created the road dataset, and we extended it with logical requirements. So what is the road dataset? The road dataset is a multi-level classification dataset for autonomous driving. What does it contain? It contains a lot of videos. Actually, I think it's 22 long videos, 8 minutes each. And each one of them has been annotated in the following way. So for each frame, we have all the bounding boxes, one bounding box for each of the relevant agent in the scene. And then for each bounding box, we have annotated the agent that is in the bounding box, the set of actions that this agent is doing, and the set of locations. So for example, we can have a pedestrian that is on the pavement and at the bus stop and that is waiting to cross. So once we have this dataset road, we annotated with the requirement What do the requirements define? Well, they define the space of admissible output. So some example of constraints are a traffic light cannot be red and green at the same time, an agent cannot move away and move towards you at the same time, or an agent is either on your left or on your right, it cannot be on both sides. Notice that as humans, we also have more background knowledge than these simple basic constraints, such as a pedestrian should only cross at crossings, or they should always stop when the traffic light is red. However, these constraints are not always satisfied in practice, while they should be in theory. And so we didn't want to add these as constraints because we really wanted to have just a set of requirements that we were sure that are always satisfied in the data set. So the first question we asked ourselves were, how often actually neural networks violate this very simple requirement? And the answer, the very surprising answer to this question is, you can find it on the left-hand side. So we tested actually 6 state-of-the-art models on this data set, and we trained them on this data set, and we saw that no matter the threshold, so by threshold I mean if the predicted number between 0 and 1 is inferior than the threshold, then we consider the label as negative, and if it's major than the threshold, then we consider it positive. So if the neural network has mean 0.8 for pedestrian, then I consider the pedestrian to be in the bounding box with a threshold of 0.5, let's say. So let's go back to our chart. So as you can see, what this chart is telling us is that no matter the threshold, at least 90% of the predictions, more or less, will present at least one violation. This was very, very surprising to me. So I checked these results like 1 billion times because personally I was expecting some predictions, some violations, sorry, but I was expecting them on the range of 10, 15, maximum 20%. Seeing these super high numbers was really shocking. However, it kind of makes sense after it kind of started to make sense in, after a while, because essentially what happens is that in a lot of cases when neural networks are tested against requirements, people test them against 1 or 2 requirements. So obviously you have a very tiny number of predictions that violate the constraints. However, we have 243. So as increase the number of the requirements, obviously the number of violations starts increasing. So on the right-hand side, on the other hand, you can find the percentage of violated requirements. And this was, I plotted this because I wanted to make sure that there wasn't an easy fix. What do I mean by an easy fix? It means that maybe the neural networks were just violating 1 or 2 requirements, and so we could engineer our way out of the problem, right? However, as you can see, the neural networks actually violate most of the requirements. Now, this sort of descending slope is to be expected because most of our constraints are actually mutual exclusivity constraints, and so they are violated mostly for obviously low thresholds, and we have very few that tell us, oh, look, you need to take a label, and you need to have at least a label or 2 labels in a subset, which obviously are violated for higher thresholds. So these are the quantitative results. I just want to give you also some qualitative results just to give you a flavor of what can happen. So in the first image, we have, for example, a pedestrian that moves away and towards you at the same time, and the neural network thinks that it's both on the left pavement and the right pavement. In the second image, we have a traffic light that is thought to be red and green at the same time. And finally, in the third image, we have a cyclist that is also a pedestrian. Now, as you can see, none of these mistakes would be done by a human, and most of all, some of these mistakes can actually lead to very dangerous situations. Let's take, for example, the image in the middle. Imagine you have actually an autonomous driving vehicle taking a decision on the ground of this prediction over here, telling you that the traffic light is red and green, with all these pedestrians passing in front of you. Now, this is the perfect recipe for a disaster. So I think this actually clearly showed us that we need to start to have constraints into the training of the neural network. So what did we do? What we did was to propose some very simple baselines so that people, if the people want to use our data set, we can actually compare the results against this available baseline. So the first baseline we proposed was to incorporate the constraints during the training phase in the loss function. Now, what's the advantage of this approach? Well, the advantage is that the neural network can learn from the constraints, right? Because they are incorporated in the loss function. However, there is no guarantee that the constraints will be satisfied. Another set of baselines was to include a post-processing phase at inference time, which essentially gives us the advantage that the constraints will be guaranteed to be satisfied, but has the disadvantage that the neural network is unaware of a post-processing step. Notice that these two approaches are also not mutually exclusive, so we also tried to use them together, and this is when we got our best results. So these are the results that we got with our 6 state-of-the-art models, and these are like if we just train them normally. And these are our baseline models when we use both the training, the constraints at training time and in the post-processing phase. So what's really nice about this table is that this model over here, the neurosymbolic one, is guaranteed to satisfy the constraints, is actually learning from them. And despite the fact that it's guaranteed to be set to satisfy all our requirements, is also outperforming the standard model. Again, proving that we can achieve, like, we don't need to get a to choose between safety and performance, but we can actually use the background knowledge that we have to define the concept of safety to actually improve our model. So now just some open questions for those of you that maybe want to start studying this problem. So these are some open questions that we still have in this field. So the first problem is, how can we integrate even more expressive constraints? The second one is it possible to create models which seemingly integrate hard and soft constraints? So for example, in the example of autonomous vehicle, can we teach the neural network that the traffic light cannot be red and green at the same time, so hard constraint, and also teach to it, look, a pedestrian should always be crossed at crossing, but it can happen that this is not the case. So another one is that, I don't know if you noticed, but so far we have just talked about constraints over the output space. Can we start also having input-output constraints? And finally, the broadest question is, can we extend this approach to other problem types? A final remark also is that like dealing with hard logical constraints is a very new topic. So we started studying it 3 years ago. Now there is another group in Edinburgh studying it. And I think that and some other people in Germany. But it's a very new topic that is currently gaining a lot of traction. And there is a lot to do, essentially, and a lot of things to discover. So it's a topic that I encourage a lot of people to actually pursue. So with this, I conclude. I thank you very much for inviting me. It was very nice to be able to present my work, and I'm very open to any questions.
Thank you very much for your talk and this last issue. Yes, so I will leave the floor for questions. You can either write them or ask them directly to Eleonora for the different parts. Otherwise, I have some to introduce maybe the discussion. Okay, it's okay. Yes, so you mentioned that for the need for the data set at the end, the Roger, was because you couldn't validate the use cases in a way that is realistic and critical. So the first data set that you used, how can you ensure that the results are coherent or make sense? And because for me, they were already good fit for your research, no?
So I think like what I meant is that I wanted something that was actually safety critical. So I wanted a data set that was able to prove us that a simple mistake made by a neural network can actually cause a lot of harm. Because I don't know if it happens to you too, because like you're kind of doing very similar things. But a lot of people, especially like pure machine learning people, what they tell you is like, oh, but if I violate this constraint once or twice, how would it matter if I have a performance of, let's say, accuracy of 99.9%? So I wanted to really take a data set where we have, okay, look, we are in autonomous driving. If you're telling me that the traffic light is red and green at the same time, then this will be a problem.
Okay, so how do you talk about cases, there are in engineering when they design material or in what we call a software product line, where they design for planes or trains, they try to find the right optimization for the hyperparameters, machine learning models. And I think they have cases where the machine learning model are predicting some parameters and it can be critical. And because it's physical system, I think they can also have natural constraints that happen there. But just an idea because
no, I mean it would be nice. Like my hope is that actually, like now we have some proposals out there. Is that in the future data set will always come with requirements. So like what in my ideal world we would have, yes, that especially safety critical scenarios, you try to build models that have the highest performance, but at the same time you have certain characteristics that must be matched, which is the case, for example, for any engineering project, right? You just don't tell the engineer to build like this, I don't know, 30th possible bridge. You also have like stress tests and everything, right?
Exactly.
So
a requirement that can be very well constrained. Yes, thanks. There is a question in the chat. I don't know if you can read it or I can read it for everyone, for the audience. How do you ensure the quality of the constraints for ROD are domain experts or human annotators?
So like we did it all by hand and we double checked. There were many like different, I annotated them and then they were double checked by other people, but these were like very basic constraints. And we also did the double check of having like the ground truth always satisfying our constraints. So we actually used the SAS solver to make sure that the ground truth always was satisfying the constraints. Actually, this was interesting because when we were doing this check, we found actually mistakes in the ground truth annotations. And to ensure like compatibility, then we dropped some of the requirements. So for example, we want to find the constraint move away and move toward, like if pedestrian cannot move away and move towards you, because there were two instances of ground truth which were annotated with both move away and move towards. So that's another proposal we have, is to start using the requirements also at annotation phase. So this requirement specification should be the very first step that people do even before creating the data set, so that you don't have to manually check also all the ground truth annotations. You can actually build checkers like SAS solvers, use SAS solver to ensure that everything will work out fine.
I was wondering on slide 42, when you mentioned the issues of negation plus circularity, do you have an example in real world where you have these cases that could not be supported? Because
do I have what? Sorry?
An example, practical example of a case where this may arise?
I think like in RODAR, we have multiple, because essentially what you have is if I don't have something, then I must have something else, and it's vice versa, right? So for example, if you take also the case of a softmax, right, with just two elements, then it would be this, exactly this case.
But if you do it only once, there is no circularity, or do you look through all the constraints? So is it symmetric or
No,
something?
it depends how you, it's exactly, in this case, it would be exactly symmetric. So for example, now, well, this is under submission, but what they've done is to find a way of exploiting both of these constraints, because obviously you could just enforce one of them, which would be okay. However, you wouldn't be guaranteed that if you don't have the head, then you will have the body, right? So it's very much a project that is growing with time, because as you expand, as you know, like in logic, as you expand the expressivity, the complexity of a problem grows too. So like when you allow for these circularities and for the negation also in the head, then you get full propositional logic. Now, full propositional logic, even the satisfiability, is an NP complete problem. So it starts to become more and more complex.
It makes sense to extend it gradually.
Yes.
Thanks. Any more questions in the chat or in the room? Few more minutes. I don't know if Maxime is here for the next talk.
Yeah, if you can hear.
So, just to show for Eleonora, we are recording the talk. Is it fine for you that we put it on YouTube afterwards? If it's fine, I should have asked you before. But,
no, it's okay. It's perfect. Thank you very much, actually, for having me. So it was very nice.
Okay, so I guess we can move to the next talk, and I would like to thank you again, Eleonora, for your work and your participation to the seminars, and to be my first guest on this seminar, and looking forward to meeting you again, and we'll discuss in a few weeks as well, because it's really a topic of my interest. Thanks. So for our last talk, it's very related. So Maxime is sharing his screen, and I will let him introduce himself.
Okay, thank you, Salah. So I would like to say first that it's a real pleasure to have this opportunity to present you the work that we've been doing in our group. So before digging into the topic, I would like to speak a bit about me and more largely our research group. So I'm from Luxembourg. So Luxembourg is a very small country in Europe, situated between Belgium, France, and Germany. We are part of the only university in Luxembourg because it is a small country. It's a pretty young university. It's less than 20-year-old, but it was designed to be primarily a research university. And thanks to that, Luxembourg managed to attract, I would say, established researchers in different fields and managed to build some kind of nice reputation, especially in some dedicated fields like material science and software engineering. So within this university, there are 3 faculties, which are mostly dedicated to teaching with a bit of research. And then you have 3 interdisciplinary research centers, which, as the name suggests, are focused on research. We are part of one such center, which is named SNT. It stands for Security and Trust, and it means to conduct various research that aims to increase the security and the trustworthiness of IT systems in general. So the research that the center does goes from cryptography to software engineering, going through signal processing, etc. So it's really broad. Still, what unifies SNT is a peculiar vision, which I think is also similar to what Riken is doing. So, of course, the SNT Center has for mission to conduct academic research of excellence, but also at the same time, we have the dual mission of supporting the society and the industry. And we do that via a lot of joint research projects with companies and public institutions. This is a bit important for this talk to understand this, because the origin of the research I'm going to present actually stems from a partnership with a specific company in Luxembourg. So within SNT, we have our group, which is on security, reasoning, and validation. We are roughly 40 persons, a bit more now. We are 4 permanent scientists, 8 postdocs, 27 PhD students, and 3 research engineers. And because of our large size, we do research on a variety of topics, which includes AI and machine learning, also software engineering, which is actually the original research area of the group. But then we also have side activities on system verification and optimization, as well as Internet of Things. But our 2 major research areas right now are machine learning and software engineering. And then, as I mentioned, because of SNT's mission, we apply our work in collaboration with different companies spanning over different fields like finance, manufacturing, energy, but also public services. And then finally, within this group, you have me. So I'm a permanent scientist of the group. I'm working on AI and software engineering and their intersection. I have the pleasure to supervise 7 PhD students and 2 postdocs. I'm also a scientific coordinator for a new research center on financial technologies. Now my research interests are mostly about machine learning security and testing, which is the focus of this talk today. Because of my origin in software engineering, I'm also interested in applying machine learning to software engineering, and in particular developing machine learning models for programming languages. And then before all this, my initial research topics during my PhD studies were about formal verification and a specific technique to verify software that we name model checking. And then I had the opportunity to collaborate with multiple companies in finance, energy, and public institutions as well. So that was a brief introduction of my background. Now we will dig into the most interesting part of the talk, I would say. So I'm going to talk what I would like to name adversarial examples in the real world. So all this work starts from evasion attacks and adversarial examples. I guess most of you are already acquainted with that. So the idea is that you have some machine learning model performing some task, could be image classification, for example, and then you start from an original example. For example, the picture of a panda that the model predicts correctly with some confidence. And then with evasion attack, it was discovered that if you add a very small noise, small but specific noise, that if added to the original examples, create a new example, which still looks the same to human eyes, but because of the noise, the machine learning model predicts the class of the image incorrectly. And it can even do so with a very high confidence. So, I mean, I guess there is no need to dig more into that. But then adversarial examples are not limited to images, as you know. You also have adversarial attacks on text, on sound as well. So you have this famous example where you have some audible sound that is paraphrased as "the boy looked at the horizon." I cannot make it listen to you because I have a headset. But then Nicolas Carlini and Wagner showed that if you had an invisible noise to this sound, you get a new sound which humans hear completely the same, but a speech-to-text system will translate it completely differently. And then you had some funny people who are trying to bridge the gap between adversarial examples and the physical world, and they started to see if they could generate a concept of real-world object you could put on your face in order to avoid, for example, face recognition system. This research is still in its infancy, but I think it's interesting to note that people are trying to see if we could transfer adversarial examples in the real world as well. So one of my important research focus today goes along the same line, except that I do not target the physical world per se, but what I would name generally the real world. So I want to study if adversarial attacks and adversarial examples are a real thing if you apply them not directly into a model, but more broadly on a complete real-world software ecosystem. So, for example, one of such real-world systems that we have investigated are financial systems, because we have a lot of partners in finance. And in such financial systems, when they use machine learning, they do not take as input images, they take financial data. So typically, you have transactions that could compose the history of some bank customers. And then you often have to make decision based on a new transaction that the customer wants to perform. So this new transaction could be a new payment that the customer would do. And in this case, you want to assess whether this new paid transaction is a fraud or is legit. The new transaction could be a credit request as well. So you have many examples where banks and other financial institutions have to automate decision based on some customer history and a new action this customer wants to perform. And then they typically, they follow, to do this automation, they follow the typical process of taking all these data and then building a feature vector. It can be done via classical machine learning where you do explicit feature engineering, but you could also use deep models in order to learn automatically a feature representation. Nevertheless, once you have these feature vectors, you can train a model, and then the model would make a decision to accept or reject the incoming transaction. Now think a bit about what would be an evasion attack in this case. So here, the goal would be to make the smallest change in the new transaction or the new credit request such that the model decision changes typically from reject to accept. So the use case, the concrete use cases we investigate here is if you take a fraud detection system and there is a fraudulent transaction that the system rejects, how could the frauder change the transaction in a way that the transaction still achieves its intended effect, but the system accepts it? Another example would be for credit scoring or credit lending. If you have a customer that requests a credit and it gets rejected, how could this customer slightly change the credit request in order to get it accepted? And of course, in both cases, it creates a danger for the financial institution, because in one case, it would mean making a fraudulent transaction pass, and in the other case, it would mean lending money to a customer who will likely not reimburse the credit. So all these examples to say that machine learning software, and it's not a surprise to you, can be inaccurate and fooled. And it can also happen in the real world. And it's important to study real world cases of evasion attacks and other security issues, because regulations are coming next. I appreciate the fact that we are not from the same part of the world, but I would like to mention that in Europe, there is today a lot of fuzz about regulating AI and putting in place the legal framework needed to surround AI systems that would be deployed in reality. And so in 2019, the European Commission first released some ethics guidelines for trustworthy AI, which were some guidelines regarding the properties that AI systems should satisfy in order to be considered ethics. And interestingly, you can observe that our research, I mean, not only mine, but also yours and the research of everyone else in the world, has influenced these, the definition of these guidelines, because you can find explicit topics that relate to robustness, safety, also fairness, which is a trendy research topic in machine learning and AI. And then later on, these ethics guidelines inspired what we call the European Union AI Act, which is a document specifying what AI providers and users should do in order not to be liable in case of misbehavior of their AI. And this AI Act is in the process of being translated into laws, into a law in all the different European countries. And I think what is interesting about this act, if you have a detailed look about what it contains, is that it explicitly demands the AI providers to put in place an appropriate quality management system. So it's a kind of self-certification process where the providers are themselves responsible for checking the quality of the AI system they build. And obviously, this should not stop at the pre-market stage, because once the system is run in the field, it remains essential, according to the AI Act, to monitor that it continues to behave correctly. And finally, the last point about the AI Act that I want to emphasize is that this quality management process and system is concerned not only with the machine learning model and its dataset, but it's concerned with the full source code surrounding that. So in case of audit, the AI providers or the companies deploying AIs should provide the auditors the full source code of the software ecosystem and not only the model, which again motivates me to study security threats of AI and machine learning, not only from the specific point of the model, but by taking the software system as a whole. But still, we need to start somewhere. So we have, in the recent years, investigated two concrete research questions. One is, are real-world machine learning software vulnerable to evasion attacks? So we will still focus on the machine learning model itself, but we will try to consider the influence that the surrounding software ecosystem has on its robustness, basically. And then the second question is how we can effectively defend this software. And of course, we will investigate adversarial training and adversarial hardening in general, but again, we will do so under the prism of the real-world constraints that this system can face. Just a reminder of how the typical evasion attacks, so algorithms to generate adversarial examples work. So you have, for example, gradient-based attacks, which tries to lead an initial example to high loss region of the model by iteratively modifying this sample. So the objective of this attack is to find in the end a perturbation delta such that if you apply the perturbation to some original example, you would change the classification result, and the distance between the original example and the perturbed example is below a certain threshold. So I'm going fast on this because I guess this is well known to you. But then now we have tried to study evasion attack in real world software. And what I mean by this is that we really consider the perspective that a machine learning model is integrated within a larger software systems, and the difference between classical image classification models that takes as input images. Here we consider a system that takes as input, you could say, more complex or more structured domain object. So in my financial system example, the domain object could be the transactions that compose the customer history, but also the new transactions that has to be accepted or rejected. And what is interesting is that these domain objects, they have to satisfy some natural conditions that are inherent to the real world object they represent. So a simple example is that a transaction should have a positive amount, because a negative transaction does not make sense. But of course, you have some more complex examples that could be based on how a customer has reimbursed previous credit, for example. And then, as mentioned before, these domain objects, in order to be classified, they are transformed into feature vectors. And these, in the same way that domain objects have to satisfy natural conditions, these feature vectors have to satisfy a set of constraints. So these constraints may originate directly from the natural conditions. So for example, if a transaction object has to have a positive amount, then the feature from the feature vector corresponding to the transaction amount has to be positive as well, kind of obvious. But you may also have constraints that originate from the way the feature vector was engineered. So for example, in the case of credit lending, there is an intrinsic link between the installment, so the amount of money you have to reimburse every month, and the total amount of credit and the interest rate. So you see that this engineered feature, the installment, will be constrained by the value of the interest rate and the credit amount. So all this to say that if you would like to apply an evasion attack to the feature space, then you would need to satisfy a set of constraints in order to be realistic. And actually, this is what we checked. So the first check that we did is that we took some real-world feature vectors, which originated from transaction requests in a real-world financial systems. And then we tried to apply some adversarial noise using standard classical evasion attacks. And then we try to feed that into the software system. And what is interesting is that software systems in general have at multiple places some input validation processes where they check that input constraints are satisfied. And when a constraint is not satisfied, then the transaction in this case is denied. So concretely, if I had an initial credit request, and then I add some noise in a way that the requested amount of credit is negative, then this request will not even reach the machine learning model. That's actually what would happen. And then we have assessed empirically on a real-world system whether traditional evasion attacks could actually succeed in generating at least one example, and they never managed to do so. So this was published to ESEC-FSC, which is one of the top 2 software engineering conferences. And we have showed basically that if you execute evasion attacks on a broader software system, it will not work because of the constraints. So what happens behind the scene is that if you consider classical gradient-based attack, and then if you represent the constraints on the feature space, the constraints are like dividing the input space into 2 parts. So the red part represents inputs that do not satisfy the constraints, and the green part represents inputs that satisfy the constraints. And what happens if you apply PGD or other traditional attack is that it always or almost always lead the original sample to high loss region, which are in the invisible part of the input space, which does not satisfy the constraint. So this is why we had this 0% success rate before. So then we argued that in addition to the objective of misclassification and minimal perturbation, we need to add to these attacks a third objective, which would be that the perturbed example should satisfy the feature constraints or the domain constraints, or more generally. So our idea was to investigate whether we could drive PGD and other types of attacks towards region of the input space which remain feasible, realistic, meaning they satisfy the constraint. So this was our contributions public at IGCI 22. So we have proposed what we call a unified framework for adversarial attack and defense in constrained feature space. So it's a unified framework because it can be applied to multiple domains. So we consider both attack and defense. So typically we consider as well the effect of adversarial training. And then what is important to note is that we focus on constrained feature space. So it still works at the feature level, but we take into consideration the constraints that are inherited from either the natural conditions or the feature engineering process. So we do not work on the domain object space directly, but I can say a bit more about that later. So now more concretely, we have 2 types of contribution in this work. One is that we have defined a generic constraint language using which you can express constraints over features. So it's typically used for tabular data, obviously. And then we have a translation from these constraints to some function that we will use to check the constraint satisfaction, basically. And then next to this language, we have investigated 3 types of new algorithm for revision attacks that are meant to satisfy the constraints. And they do so with varying success, as you will see. So about the constraint language, I would say it's a typical constraint language, nothing very fancy in that. So you have typical operators to build constraints like conjunction, disjunction, numerical comparison. And then the elements that you can compare are constants, feature values, or basically their linear combinations, basically. So nothing very unusual. What is perhaps a bit more interesting is that we have defined a translation from these constraint formulae to penalty functions that we can use to assess whether some examples satisfy the constraint. So the idea is that an input X will satisfy a constraint omega if the corresponding penalty function evaluated on X has reached 0. If it is the case, then X satisfies omega. And if it is not the case, the penalty function will return a positive value. What is also nice to note is that this language that we have defined it in a way that it is sufficiently expressive to instantiate constraints that we have observed across different domains, like finance, network security, and also malware detection. Coming back to the last discussion that we had during Eleonora's talk, the idea was not to have the most expressive language either, because as you increase language expressiveness, you also increase the complexity of the corresponding analysis. So typically, we wanted to keep penalty functions which were as simple as possible. So this is why we are not so keen on augmenting the expressiveness of the language, which is quite easy to do. In the end, it's just formalization. But we still want this to be able to work operationally on this language via the penalty functions that we have defined. So it's a sufficient but not too much expressive language. And we will extend it based on needs on an opportunistic manner. So now let's talk a bit about the different approach that we have tried out to enforce constraints. So our first approach is quite simple. The idea is simply to apply PGD as it exists, or any other classical attack as it exists today. And then in case we fall beyond the feasible part of the input space, so in case we have generated an infeasible example, we use some kind of projection operator to project the solution back to the feasible input space. There is no technical novelty in that. We have simply used an off-the-shelf mathematical programming solver in order to find the closest inputs to the one we have generated that satisfy all the constraints. So quite a simple idea. Then the second approach that we have investigated consists in integrating constraint satisfaction directly as an objective of PGD. So the approach is named constraint PGD. And the idea is that in addition to the loss function that PGD aims to maximize, we add a new term that you could see as a new regularization term that considers the penalty function. So the idea here is that we want to force PGD to maximize the loss, but also to minimize the penalty function. Because remember, the goal is to reach a penalty function which is equal to 0. And so to do that, we will still use gradient ascent or descent, so gradient-based optimization, in order to achieve this objective. One note, though, there is obviously a limitation to that, in that the penalty function that we have should be differentiable in order to be able to compute the gradient. And ideally, they should be convex in order to increase the likelihood to converge towards the global minimum of the penalty function, which in this case is 0 and is what we aim for. Nevertheless, so in the end, our constraint PGD approach is quite simple. It exactly follows the idea of PGD, except that we have changed the term to optimize. And then the third approach is a gray box approach where we use multi-objective genetic algorithms in order to create adversarial examples that satisfy the constraints. I don't know how much you are acquainted with genetic algorithms, but the idea is that we start from an initial population. So in our case, our population is a set of candidate examples. Originally, this population can contain the original example together with some random perturbation of this example. And then the genetic algorithms will make the population evolve. So it means that we will take the different examples, we will evaluate how close they are to trigger misclassification in the model, but also to satisfy the constraints. And based on this evaluation, we will select a part of them that we will keep, and then we will breed some new examples based on these selected examples via some crossover operators in order to produce new examples. So the idea is really to combine the different features of the examples that we have selected to produce new ones. And then we randomly apply some mutation, meaning that we randomly change the feature of the examples. And then we principle of genetic algorithms. Now, what is peculiar with our approach is that we have a genetic algorithm, a multi-objective algorithm, and we have three objectives. One is obviously to maximize the loss function in order to increase the likelihood of triggering misclassification in the model. Then we have the objective of minimizing the distance between the original example and the examples that we create. And finally, should not be a surprise, we have the objective of minimizing the sum of all the penalty functions. So meaning we want to ensure constraint satisfaction. So we have these three approaches, and we have conducted some experiments in order to assess whether they are successful in generating examples that are misclassified and satisfy the constraints. So to do these experiments, we consider two types of model, neural networks and random forest, and for different data sets. So LCLD is a data set on credit scoring. So it's a finance data set. CTU13 is about botnet traffic detection. Then we have one data set on malware detection and one on URL classification. As for the different attacks that we evaluate, we have, in the case of neural networks, PGD, the classical one. Then we have our three approaches. So PGD plus the prepare operator, where we project back the solution to the feasible space. We have constraint PGD, and then we have our genetic algorithms, which is abbreviated MOIV2. When it comes to random forest, we compare only our genetic algorithms because by default, gradient-based attacks do not apply to random forest. And for the same reason, the baseline we compare to are the papernut attack, which was originally defined for decision tree, but that we have extended to random forest. And then, so we have applied all these attacks on all the tests, on the full test set of all these data sets, and we have measured the success rate. But beware here that success rate refers not only to the capability to create misclassification, but also to satisfy the constraints. And it turns out that the classical attacks, unaware of constraints, most often fail. They actually fail all the time, except the papernut attack on the URL dataset. But this is a very simple dataset with very few constraints. And the reason of this failure is that these attacks were successful at generating misclassification, but not in satisfying the constraints. Then we have our constraint PGD approach, which worked on one dataset out of two with limited extent. It's not a huge success, I would say, but admittedly, we believe that we have not used CPGD optimally. There are still things we can do to improve it and increase its success rate, like optimizing the hyperparameter, etc. But nevertheless, at least this shows that if you introduce constraint within PGD, you may make PGD generate successful and feasible examples, but there is still room for work to improve this approach. Perhaps more positively now, the genetic algorithms or genetic algorithm has managed to create at least some adversarial examples in all models with varying success ranging from 5% to 100%. So in the end, we conclude from these experiments that while classical approaches are most often completely ineffective to create adversarial examples and attack real-world software, they can be adapted, or you can devise new approach to generate such threats for real-world systems. And because this threat exists, we wanted to investigate next how we could increase the robustness of these systems. So one obvious approach that we have applied to this aim is adversarial hardening. More specifically, we have applied adversarial retraining, meaning that we first train an original model on an original training set, then we select an independent sample of the test set. We generate adversarial examples from this sample set using our genetic algorithms, and then we apply retraining to the original model in order to produce a hopefully more robust model. So that's the typical process, nothing new. But interestingly, we had another idea to increase the robustness of the model. So the idea was that since we have observed that constraints makes it very hard, if not impossible, for classical attack to generate feasible example, couldn't we define additional yet artificial constraints in order to make this generation even more difficult? So our idea is to augment the set of constraints with a set of totally redundant and totally artificial constraints in order to increase the robustness of the model. So the approach that we have followed is quite simple. So we can take any two existing features, F1 and F2, and then we combine them into a third feature, FE, which we add to the feature vector. By combining, I mean you can use any operator. So you could use a plus in the case of numerical features. You could use XOR in case of if you use one-hot encoding, for example, or if you use Boolean binary features in general. And then with these new features that we have added to the feature vector, we add a new constraint which simply imposes that the new feature still follows its definition. So if you had FE defined as F1 plus F2, we simply add the constraints that FE should always be equal to F1 plus F2. But what it implies for an adversarial attack is that if an attack was to modify F1, for example, in order to create misclassification, it should also modify both F2 and FE to preserve the satisfaction of this constraint. So we hypothesized that this could makes it harder for attacks to work. So we have actually measured both the effectiveness of adversarial retraining and or constraint augmentation method to increase model robustness. And we conducted, again, experiment measuring the success rate, both in terms of misclassification and constraint satisfaction. And what we observed with all these results is that first, adversarial training, adversarial hardening in general remains effective in constraint feature space. So you see, for example, that if we used our genetic algorithms to do adversarial retraining, we decreased the effectiveness of CPGD by around 7% on the LCLD dataset. And then we decreased the effectiveness of the same algorithm by 12% more broadly. When it comes to the botnet traffic detection dataset, we see that with a bit of adversarial retraining, we managed to almost annihilate the capability of our genetic algorithm to attack the model, which is quite a big success. The second conclusion that we draw from our experiments is that constraint augmentation is also effective. So it's a really nice alternative defense to adversary training, especially that it does not require much computational power to augment the constraint. So we see that, for example, when we did some constraint augmentation, we managed to completely annihilate the capability of constraint PGD to generate adversarial examples. And then for the genetic algorithms, we reduce its capability by 70% in the case of LCLD and by 100% in the case of CTU30. And the last interesting conclusion is that you can actually combine both constraint augmentation and adversarial training to have an even greater effect. So this indicates that these two defenses have complementary effect. So to conclude this part of the talk, and I think given the time that it's the talk, the full talk that will stop here. So what we have done is that we're interested in studying evasion attacks in real-world software. And the first step that we did towards this is to consider the constraints that protects the system against classical attacks in the end. And to further study the robustness of these systems, we have investigated constraint attacks, which takes into account the constraint to craft feasible adversarial examples. Our experiments have revealed that the threat actually exists. It does not come from the classical attack, but from adaptations of these attacks to take into account the constraints. And finally, we have proposed constraint augmentation as a new way to increase model robustness, and a way that is also complementary to the classical robustness augmentation approach of adversarial training. Then perhaps before finishing, I would like just to tease our more recent work. I won't have time to dig into that, unfortunately, but I will be happy to discuss it further if you wish. So given these results, our next steps was to study whether we could actually make a model, a real-world model, more robust against realistic attacks by using unrealistic examples. Because there is actually a big drawback to the three approaches that I have presented, especially the genetic algorithm, is that taking into account the constraints drastically increases the computational cost you need in order to craft adversarial examples, especially in the case, again, of the genetic algorithm. So because realistic examples are hard to produce, it makes adversarial training even more costly. So what we wanted to see is whether we could find, in some cases, some unrealistic adversarial examples typically produced by classical attacks, which are more efficient. And if using those examples, we could increase the robustness of the model against the real-world threat. I will not give more details than this. We'll just say that the answer is, it depends. So thank you all for your attention. I'm happy to take on any question now or later.
Thank you, Maxime. Can you hear us?
Yes.
Great. Thanks again for your talk and for this introduction of the implication of adversarial attacks in the real world and all the considerations that we should take into account. I don't know if people have questions on the chat or they can ask.
I cannot see the chat, so I count on you to tell me.
Okay. No, there is no question.
I want to ask questions.
Yes.
Just questions. So what do you think of future perspective adversarial attacks and defense, maybe in coming next 5 years or 10 years? What's your forecast?
My forecast. Well, actually, I would feel that it's not in 5 or 10 years. It's happening now, I would say. I mean, the threat is real. There are a lot of worriness from the industry about the security threat posed by or because of AI in general. So, for example, I discussed no sooner than last week with an association of chief security officer from different companies in Luxembourg, and they are building a working group on AI security. So I think it's really important to be aware of this, because it means that the industry today is aware that there are threats coming from AI, or there are threats coming on their AI system that they would build. Now, I mean, I think there is still, for researchers, there is still a long way to go in order to be able to mimic the real threat that posed. So, I mean, the constraint attacks that I have presented are just one step. You also have problem space attacks, which directly manipulate the domain objects. And these are basically a good representation of the real threat, because if you can really create a real object that threatens the AI, it means you can attack the system, basically. Now, I mean, I think what is difficult to anticipate for research is that these problem space attacks, so the most realistic attack, they are costly to produce, both in terms of engineering cost and on computational power. So I think that the challenge for us researchers is first to build good surrogate of problem space attack that we can apply at low effort to various domains. Because I don't want to study specifically possible attack on malware detector or possible attacks on finance detector, because AI has penetrated into all the industries. So we need to, I seriously believe that we need to study all these threats with a broad perspective. Still, on the other side of the prism, there are generative attacks, as you know, that can apply to potentially multiple domains, but they also have simplistic assumptions like white box settings, access to the model, no or not enough constraints, etc. So I think that one of the big research trend that will follow, and I think it also relates to Eleonora's talk today, is to take all these real world properties that we have not considered in the past into account in order to make our work more generally more applied to the real world. So it's a very vague answer. I'm sorry about that. I hope you did not expect more precise directions, but I think that it is important to study how things happen in the real world, because this is how we are going to build more realistic assumptions that we can use to craft our different research methods.
Yeah, thank you very much. Which is very exciting and inspiring. Thank you.
Thanks. Just a follow-up question, Maxime, about this: the fact that you say that we need to confront our research to industry. I was wondering if you feel that this position is very shared by other researchers like Carlini, Peppernot, and they also have the Madri as well. They're all now focusing on this. My question here is it really our job as researchers, or is it more is it an engineering problem, or is it a research problem to adapt to the domain specification?
I would not say it's an engineering problem. It remains research in the sense that we study an open problem that does not address the direct need of the industry, and at the same time, the solution is not straightforward. So it remains research. And the work I have presented, although it was built with the angle of being useful for the real world, it's still a purely academic work, because, as mentioned, there are still some assumptions that do not fit the practice. So to me, it's not because you are interested in what the real world does that you are not doing research. If I am a bit provocative, do you think that all the research on COVID vaccine were an engineering issue? It addresses a real world issue.
Yeah, we had some scientific problem to solve for that as well. Yeah.
Yes, exactly, and that's exactly the same answer that I have. There are research problems to solve in order to provide actionable solution to the industry. It's not engineering in the sense that the solution is not known and doesn't just need to be developed. That would be my answer. Still, don't get me wrong. I'm not saying that what I would call purely academic research is not useful. If today the threats of AI can be investigated in the real world, it's because a lot of researchers have investigated them before in more theoretical settings, I would say. So typically, if PGD did not exist, I would not have created constraint PGD, right? So I think that we are living an interesting time in AI and machine learning research, in that we have very strong theoretical academic work that is done, and we have the capabilities today to bridge the gap between these methods and the real world. And what is even more interesting to me is that the real world is actually asking for this.
Any last questions or feedbacks? Yes, if there is no more questions, Maxime, you're okay that we publish your talk on YouTube?
Yeah, definitely.
Okay, so
and if there are any questions later, I'm happy to answer them via email or to have a follow-up meeting to anyone who would be interested.
Exactly. We'll update the website with the video for the talk and your contact information. So please, everyone, feel free to watch it again or get in touch with Maxime and Eleonora as well for further questions. And thanks again, Maxime, for joining on this talk, and everyone for attending.
It was my pleasure. Thank you for the invitation.
And our next talk is on the 24th around the same time, 5 to 6 Tokyo time. And looking forward to seeing you all next week. Bye-bye.
Thank you.
Thanks a lot. Bye-bye.